to the first half of the webinar on climate change. This webinar is going to focus on how does the sun interact with the Earth's atmosphere and oceans to create the planet's many climates. As we know, Earth's climate system is basically driven by solar energy, by sunlight, and as that sunlight moves in and out of the atmosphere and also moves around within the atmosphere and oceans, it creates a wide variety of climates that you can see on this image, all the way from the green rainforests around the equator, the tan areas, large deserts. We also have polar regions where you see a lot of the white at the north and southern parts of this map. So as the sun interacts with the atmosphere traps and detains a lot of the solar radiation for a time, and the atmosphere interacts with the other spheres, with the lithosphere, that is the land, with the biosphere, particularly plants and animals, with the hydrosphere, the oceans, and the cryosphere, that would be the ice, glaciers, ice sheets, and so forth. And the atmosphere itself, composed of many different gases, also has particles in it that are moving around. So we'll have particles of, let's say, aerosols, water vapor, and so forth that interact with the sun's energy as well. And so these complex interactions are well illustrated here. All of the different things that scientists need to take into account in terms of being able to model climate and understand how climate functions. And so scientists look at how the atmosphere interacts with the oceans, ice sheets, land masses, and vegetation in order to create the overall climate system. Now we're going to take a look at how the oceans move energy around. So this is moving into wintertime in the northern hemisphere, and the North Pole is basically in the shade at this point, and so we see the growing sea ice as the ocean water freezes and turns white in this particular diagram. The cooler colors are obviously cooler ocean water at the surface, and the red colors that you see along the equator are due to the uneven heating of the Earth's surface. We have a lot more energy coming in at the equator than we do at the poles. And so because of that inequality in heating, the system begins to move heat through the atmosphere and oceans. In this case, we're looking at the ocean currents. And this is an ocean current off the coast of Japan that's much like the Gulf Stream off of North America. And that warm water shoots all the way across the Pacific Ocean and actually keeps Alaska, places like Vancouver, Seattle, much warmer than they would be at their given latitudes. As we move further south, we can see along the equator a belt of very, very warm water. And here we're coming up on the Antarctic, where again we have a lot of sea ice, and you can see the movement of ocean water basically redistributing that heat. Water has an incredible ability to absorb and retain heat and to move it around. And what you also find is that where you have a lot of warm water, there's a lot of water vapor being given off, a lot of steam, and so that oftentimes has a big impact downwind where you have a lot of humidity. Here we have an image of the Gulf Stream going up the northeastern coast of North America, and that warm water shoots all the way across the Atlantic Ocean and keeps Europe remarkably warm given its latitude. And here we have another image of the Gulf Stream. So if you can imagine all of that warm water that's piling up, on the far right we can see the western coast of Portugal. To the north of that you can see Ireland, and way up at the top you can see Iceland. Those are much further north than, let's say, New York City or Boston. Iceland and Ireland should be much, much colder, but because of all that warm water that comes across, it basically results in a much warmer climate than usual. And so we can see in this diagram, this animation, that movement of warm water that's coming across the Atlantic. The red band is indicating the surface movement of water, And as that warm water travels all the way across the ocean, it's giving off a lot of water vapor, a lot of energy to warm up the climate of what would normally be a very cold northwestern Europe. But as it's giving off a lot of that water vapor, you also find that a lot of the salt is left behind. And so the surface water becomes very salty, much more dense, much heavier. And as it cools, it also becomes more dense. And so it begins to sink in the North Atlantic. And as it sinks, it actually draws up more warm water to that part of the world. And this is a part of what's referred to as the thermohaline circulation. It's basically an ocean conveyor belt of ocean water that's circulating over many thousands of years. But this is really key in terms of creating the Earth's climates. Another important aspect of climate, of course, is the movement of the atmosphere, the way that energy and particles are moved around by the atmosphere through winds. And those winds, here we have a global scale model of winds, and basically it's showing us the water vapor. The red colors here indicate parts of the atmosphere that have a lot of water vapor. The, let's say, lighter blue, purple to kind of a brownish color are places that have a lot less water vapor in them. And so the atmosphere also plays a really important role in terms of moving energy around the Earth's surface, and water vapor plays a big role in that because, again, water has a great capability for moving energy from one place to another. Here we have a global scale model of wind patterns around the world. And this is also showing us water vapor and clouds, cloud cover. This is from the National Center for Atmospheric Research. And this is basically a model that shows you, how the distribution of water vapor plays a big role in the different types of climates that are developed in different parts of the world, and also the seasonality. Here we're towards the end of September. It's about the same time you're going to be in Vietnam. Vietnam is underneath the clouds completely this time of the year, whereas Bolivia is actually in its dry season, just going into the rainy season. If I were to switch this back to another part of the year, let's say in March, that's sort of the opposite end of the year, where we have a lot more moisture further south, and it's going to be somewhat drier north of us. And so the Earth's atmosphere plays a vital role in terms of moving material around. And the way in which the scientists model that climate to understand it better is using global circulation models, in which basically they break up the planet into grid cells, going all the way from the depths of the oceans to the edge of the atmosphere. And these grid cells, each one of them are assigned, let's say, a particular characteristic, and the grid cells will interact with one another based on equations. So if you can imagine, here we have all of the different interactions between different parts of the atmosphere, lithosphere, cryosphere, etc. As the solar energy comes in, as the sunlight comes in, sometimes it's reflected off, sometimes it remains in the atmosphere, it's detained. You have all kinds of interactions between water and air, between land and water. You also have interactions with the biosphere, with the plants, absorbing a lot of energy and creating fuel out of it. And all of this is modeled using these global climate models. But one of the limitations of these models is the resolution, the fact that a lot of times these models are at a fairly coarse resolution. The grid, let's say the grid is basically at 200 kilometers on a side for each of these cubes. And so that sometimes simplifies what the models can show. For example, a very, let's say, complex mountain range can be represented as simply a flat plateau, as you can see on the left side of this particular model. If we were to take a look at global climate models at a 200 kilometer resolution and then compare that to let's say a downscaled, more regional model that's maybe has pixels or grid squares at 1/8 the size, you can see the dramatic difference between the amount of information that you get, the fine-tuned, let's say fine-grained information that you can get from these models. But despite the fact that these models are at a global scale, they're still quite useful for modeling climate. Here we have a model of global winds that is showing you aerosols. Aerosols are basically particles in the Earth's atmosphere. Most of the time these will actually shade the surface and actually, let's say, reduce the amount of energy coming into the Earth system. It'll oftentimes reflect the energy back out to outer space. So we have dust, for example, the orange-red coming off of the Sahara Desert. You can see sea salt coming, basically the sea spray, and then the water will evaporate and leave salt crystals in the air as a light blue color. You can see particularly around Antarctica. Organic and black carbon are modeled here in green to yellow to white colors. And so you can see in the middle of the rainforests of South America and Africa, for example, large amounts of burning of biomass is giving off a lot of black carbon. You also have sulfates, which is basically pollution coming from cities, the white color, ash brown to white, coming out of the major industrial centers of North America, Europe, and East Asia, China and Japan in particular. The white colors are basically large plumes of pollutants coming out, sulfates. The yellow and red dots are wildfires or human-initiated burns. And we have one more animation here that shows in detail the same aerosols, but this is on a globe. And you can see that the atmosphere is constantly circulating these around and moving them around. Again, most of these aerosols, these particles, are reflecting, let's say, the incoming sunlight and doesn't allow that sunlight to be retained in the Earth's atmosphere. For example, when Mount Pinatubo in the Philippines erupted in 1991, there was so much ash erupted and so many sulfates erupted into the atmosphere that actually cooled the Earth's atmosphere for a number of years afterwards. But then we also have the carbon, particularly carbon compounds and carbon gases that trap heat, actually. They're heat-trapping gases, what are known as greenhouse gases, that we're going to talk about in more detail in the second section of this webinar.